Hi everyone, I'm Jason. Today I'm going to introduce AlphaFold3 revolution in predicting protein-protein iterations. Let me start by defining what is protein-protein iterations. Protein-protein iteration refers to specific and intentional physical context established between two or more proteins to carry out specific biological activity. We can think of it like a molecular docking, two proteins coming together and form a functional complex. Why are protein-protein iterations so crucial? Actually, they drive signal transduction, enzyme regulation, and immune recognition. Essentially, PPI are how cells communicate and function. To truly understand how this iteration works, scientists need 3D structural information or PPI. However, here is a problem. There are approximately 600,000 PPS inside human cell, but less than 5% of it have structural information. The reason why there is such huge gap is because the traditional method is expensive and time-consuming. Let's take X-ray crystallography as an example. It takes months to years and costs around 150,000 to make a single 3D structure. So scientists need a way to predict the 3D structure instead of using this experimental method. So they invent AlphaFold3. Scientists can input multiple protein sequences, and AlphaFold3 will provide a 3D image for the protein complex. The whole structure can be divided into three main parts. I will explain one by one. For future instruction, a genetic search conducted first. Genetic search provides multiple sequence alignment for protein. Here is an example about the MSA. You can see that MSA consists of a protein sequence of different species like human, fish, rabbit, and chicken. If the input involves several protein sequences, there will be MSA for them. Next about template search. The pipeline search for similar existing template from PDB. Finally, for the conformer generation, a conformer feature is typically generated with a chemical machine learning package called RDKit by using ETKDG algorithm. Next is the template feature. Some of the MSA feature, conformer feature, and the input itself will be embedded by neural network inside input embedder. The input embedder has three different outputs, contains the information about the atom level, the relationship between tokens, and the token information. After we finish constructing embedding input, next part is the input processing pipeline. There are three parallel modules. First, the template module is used to encode the template feature. MSA module is used to encode the MSA feature. And the output of these two modules will combine with pair feature and go to pair former. The single token feature will go to pair former as well. Pair former is the reasoning engine for AlphaFold3. It analyzes all input features and decides how proteins should fold and iterate with each other. Notice that the recycling mechanism at the bottom. The refined representations feedback as an input for multiple iterations, progressively improving final output. Now let's look at how AlphaFold3 generates the final 3D structure and evaluate its quality. The refined representation from pair former fit into diffusion module. The module starting from random noise. Then it progressively denoise the coordinates over multiple time steps. At each time step, it predicts how to move atoms closer to their true positions. Notice that this module has similar recycling mechanism with pair former to make better prediction. There is a confidence module evaluates prediction quality. This tells us which part of the prediction are reliable. Now let's check actual performance of AlphaFold3 in PPI prediction. In 2024, Rui's team done some testing about this. This is their result. The Pearson correlation is an evaluation about prediction accuracy. If it's higher, the accuracy is higher. AlphaFold3 ranked score achieved 0.49 Pearson correlation, which is significantly larger than the performance of AlphaFold 2. However, AlphaFold 3 isn't the best method in prediction. There is another method called SSIPE achieved 0.68 Pearson correlation. One key point of this testing is when the researcher compare AlphaFold 3 with other methods. All methods improve their performance. Let's take a look at the diagram. The first row, the original Spearman correlation is 0.62. However, after the researcher apply AlphaFold 3 on it, is the Spearman correlation become to 0.7. Now we know that the effectiveness of AlphaFold 3 in the prediction. This study published just in this year in the Virus Evolution shows how AlphaFold 3 improve the vaccine production. There is a challenge about vaccine production. Vaccine producer needs 6 months to produce the flu vaccine, but during these 6 months, the flu virus has undergone mutation in its surface protein, producing different PPI with human cells. This will cause the effectiveness of flu vaccine is lower than 50% because when the vaccine reaches to public, the version of the virus has already updated, so the effectiveness is lower. Here's where AlphaFold 3 changed the game. Research can input the mutated virus and the human cell. Within a few minutes, AlphaFold 3 will predict the 3D structure of the new complex structure and estimate how mutation affect the binding strength. This will accelerate the production of a vaccine. Actually, AlphaFold 3 performs well in this task. When researchers compare AlphaFold 3 predicted structure against to the experimental crystal structure, you can see the diagram here. The Pearson correlation decreased by only 1.1%, which means the predicted structure is very close to the actual structure. The more importantly is when they test on the HK.3 variant, which wasn't in the training data, the AlphaFold 3 achieved a correlation of 0.81. This is quite important because it proves that AlphaFold 3 can predict the mutated PPI. Now the vaccine producer can trust the result provided by AlphaFold 3 and accelerate their speed to produce the vaccine. This is my reference. Thank you for your attention.